Okay, Math 8 students, here we are in Lesson 10.2, Algebraic Representations of Dilations. Building off of what we did in Lesson 10.1, which was properties of dilations, we are now determining how we represent those properties algebraically. So, taking a look at our essential question, we want to think about, this as we go through all these explore activities, and so hopefully by the end of this we can answer this essential question, which is, how can you describe the effects of a dilation on coordinates using an algebraic representation? So using an equation, that's what it wants to know. So taking a look here at Explore Activity 1, we are graphing enlargements. So when a dilation in the coordinate plane has the origin as the center of dilation, so this works when the origin is the center of dilation, you can find points on the dilated image by multiplying the x and y coordinates of the original factor by the original figure by the scale factor. Okay, that's that ratio that we determine. For scale factor k, we're going to use k as our scale factor. The algebraic representation for the dilation is so the original coordinates x and y, and then you would apply that scale factor of k times x and k times y. And so that works for enlargements when k is greater than 1. So when k is greater than 1, that's going to give you an enlargement. So you're multiplying your scale factor times your x and y coordinate. So we're going to go ahead and actually do that now. We're going to take the figure shown below on the grid, which is the preimage, and the center of dilation is the origin, right? So that's telling us that we can use this rule right here, because the center of dilation is our origin. So first thing we're going to do is list the coordinates of the vertices in the preimage on the first column on the table. So I'm going to go ahead and scroll up here. Okay, and it doesn't have these vertices labeled, so I am just going to go ahead and label them because it makes me know that I've got all of my vertices listed. So A, B, C, D, E. We'll call this one F, G, and H. And I'm just going to go ahead and write these here on the column. F, G, H. Okay, so now I know that I've got all of them. And then this will be the image. So this would be A prime, B prime, C prime. And so it doesn't ask you to do this, but this is just kind of one of those things that helps things stay a little bit organized and keeps things in order and make sure that you're writing down the right corresponding vertices. So A was done for us, and that coordinate is 2 and 2. So we're going to go to B, which is 2 and negative 1. C, which is 1 and negative 1. D, which is 1 and negative 2. E, which is negative 2, negative 2. F, which is negative 2 and 1. Oops. G, negative 1 and 1. And H, which is negative 1 and 2. Okay, so those are my preimage coordinates. That's for all my coordinates for my vertices of this figure here. And now what it wants me to do is determine the scale factor for the dilation. Well, the way I'm going to do that is I'm going to go ahead and look at my algebraic expression here and notice that I've got 3 multiplied by my x coordinate and my y coordinate. So that actually means that my scale factor is 3. Okay, because I'm taking my original, I'm multiplying it by 3, I'm making it 3 times as big, so it's an enlargement. And that's how I get my coordinates for my image, for my dilation. So I'm going to take each of these coordinates, multiply them by 3, and that should give me the coordinates for my dilation. And that's actually what it asked me to do here in C, is apply the dilation to the preimage and write the coordinates of the vertices of the image in the second column. Okay, so 2 times 3 is 6. Negative 1 times 3 is negative 3. Okay, I'm going to just go through this. 1 times 3 is 3. I need my parentheses here. Negative 1 times 3 is negative 3. 1 times 3 is 3. Negative 2 times 3 is negative 6. Negative 2 times 3 is negative 6. Negative 2 times 3 is negative 6. Negative 2 times 3, negative 6. We got a lot of those. And then 1 times 3 is 3. Negative 1 times 3 is negative 3. And 1 times 3 is 3. And then negative 1 times 3 is negative 3. And 2 times 3 is 6. So now I've got all my coordinates for my image. And I got those from taking my pre-image coordinates, multiplying my algebraic representation, showing my my scale factor of k, which is 3, and multiplying that by my original coordinates. Okay, so now that I've got my image coordinates, I can actually graph my dilation. And I know that since my k, my scale factor k here is 3, since it's larger than 1, this is going to be an enlargement, right? So it should be bigger than my original, right? Okay, so I'm going to go ahead and graph those. So I'm going to start here, and I labeled these. You didn't have to, but it just kind of makes it a little bit easier for me to keep track of them that way. So I've got my A prime, so I know it's going to be over here somewhere, right? And I've got 6 and 6. So here's 7, so 6 and 6. And then I've got my B, which is 6 and negative 3. 1, 2, 3. Then I've got 3 and negative 3. And that's my C prime. And D, negative 3, negative 6. Okay, I'm just going to keep going, just going down my list. Negative 6, negative 6, negative 6. And F prime is negative 6 and 3. And then G prime, negative 3 and 3. And then negative 3 and 6 for F prime. Okay, and then I'm going to go ahead and just connect my points now. I didn't label these. I should label these F prime, G prime, H. And I'm going to connect all my points. I should have a similar shape, right? Same shape, different size. And so if I don't, then I need to double check, make sure I got my... And I've got my shape, and it is an enlargement, and it's got a scale factor of 3, so it should look bigger. And I made the points, and I got my corresponding points. So how does the dilation affect the length of the line segments? So we know that kind of from our previous experience with dilations in lesson 10.1 that line segments will have the same scale factor or the same ratio as coordinates, right? So that means that the side lengths should be 3 times the size as the corresponding sides in the pre-image, right? And we can just take a look here. Let's just double check that. We'll go back. And so if I've got a side length here that's 3, AB, my side length here should be 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, because it's 3 times enlarged, right? So my side lengths will also be 3 times as long for each corresponding side. So let's go ahead and say each line segment in the image, which is the dilation, is 3 times longer than the corresponding line segment in the pre-image. Oh, I can't spell corresponding. Corresponding building the pre-image. Okay, and then the second question it's asking us is, how does dilation affect angle measurements? Dilation does not affect angle measurements, because if the angle measures are changed, then you're going to have a different shape. And we know that dilation does not change the shape, it only changes the size. So dilation does not change angle measure. Okay, so we are moving on to explore activity 2, and we are graphing reductions. So for a scale factor between 0 and 1, the image is smaller than the pre-image. This is called a reduction, right? So when it's smaller, it's a reduction. When you reduce fractions, you make them smaller. So this is a reduction. Reduction is still a type of dilation. The arrow shown is the pre-image, and the center of dilation is the origin. So it tells us that because that means that we can apply that algebraic rule, where we multiply our scale factor by each x-coordinate and each y-coordinate to get our coordinates of our dilation. So we're going to list the coordinates of the vertices of the pre-image in the first column on the table. So let's go ahead and start over here. Okay, and that would be 4 and 2, so that one and 2. And then you could label these like we did in the last one. You don't have to. And then I'm going to do this next point here, which is 2 and 2. And then I'm moving clockwise, and I got this point here. And it is 2 and negative 4. Right? And then I've got this one here, which is negative 2 and negative 4. And then I've got this one, and this is negative 2 and positive 2. And then this one here, which is negative 4 and 2. And then this last one here, which is 0 and 5. Okay, so now we're going to look at our algebraic representation here, and the number that's being multiplied by each of our x-coordinates is our scale factor. So when it asks us what is the scale factor of this dilation, we see 1/2. So our scale factor is 1/2. That means that this is a reduction, right? Because that's less than 1. We're going to apply the dilation to the pre-image and write the coordinates of the vertices of the image in the second column. So each of these we're going to multiply by 1/2, or divide by 2 to get 1/2. So 4 times 1/2, 1/2 of 4 is 2. 1/2 of 2 is 1. 1/2 of 2 is 1. 1/2 of 2, 1. Half of 2, 1. Half of negative 4 is negative 2. Half of negative 2 is negative 1. Half of negative 4 is negative 2. Negative 2, half of that is negative 1. Positive 2, half of that is 1. Negative 4, 1/2 is negative 2, and 2 times 1/2 is 1. And the last one, 0 times anything is 0, right? And then half of 5 is 2.5, or 2 and 1/2. So now I've got my coordinates for my image, and it wants me to graph based on these coordinates, okay? So I know this is a reduction. It should get smaller. So hopefully I have the same shape, but a different size. So I'm going to start here with 2 and 1. 2 and 1. And then 1 and 1. And then 1 and negative 2. And then negative 1, negative 2. So it's starting to come into shape here. And then negative 1 and positive 1. So yeah, I'm just going through here. So I got this. And then negative 2 and 1. So negative 2 and positive 1. and then 0 and 2.5. So I've got 0 and 2.5. And so there is my new arrow figure, and it has been reduced by a scale factor of 1/2. So let's take a look at our reflect here, and it is asking us, how does the dilation affect the length of the line segments, right? Well, this is the same as an enlargement, right? It's going to be affected in the same scale factor that we have, that we applied to each of our coordinates, right? So each side length is going to be 1/2 of the preimage, right? So the image, that's our dilation, length will be 1/2 the preimage. Okay, and then our second reflect question here is, how would the dilation with a scale factor of 1 affect the preimage? Well, if we think about this, a scale factor of less than 1 is going to be a reduction. A scale factor of greater than 1 is going to be an enlargement. A scale factor of 1 is the exact same, right? It's exact same. It's a 1-to-1. So the image and the preimage would be the same, right? There would be no change. Okay, so we're going to go ahead and move to the next page now. Okay, so we're going to go ahead and take a look at the center of dilation outside the image. We are still actually having the center of rotation as the origin, but this time the image is not around the origin. So the center of dilation is going to be outside of the image. So just real quick here. Starting right here, the center of dilation can be inside or outside the original image and the dilated image. The center of dilation can be anywhere in the coordinate plane, as long as the lines that connect each pair of corresponding vertices between the original and the dilated image intersect at the center of dilation. Okay, so we're going to take a look at example 1, where we're going to graph the image of triangle ABC after the dilation with the after dilation with the origin as its center and a scale factor of 3. So what are the what are the vertices of the image? So the origin is still the center of dilation, but the image is outside of the center of the center of dilation, right? Our previous examples, we had the shape around the origin, so this was also at the center of our shape, but now it's not. But because it's the origin, we can still apply our algebraic rule, right? Where we're multiplying our scale factor by each of our coordinates. In this case, our scale factor is 3. So multiply each coordinate of the vertices of triangle A, B, and C by 3. And that's going to tell us our vertices of our image, right? So here's our original. Here's our coordinates of our original, right? We multiply each of those by 3, and it gives us our coordinates of our image, of our dilation, right? We know it's going to be an enlargement because our scale factor is greater than 1. So our vertices of our dilation of our image are listed here. So now we're going to draw them. And what they did is they actually drew them down here for you. And it's a scale factor of 3, so my side lengths, just to double check, should be 3 times the size as the original. So if this side length is 2, this side length should be 6, right? 1, 2, 3, 4, 5, 6. And that's just a double check to make sure I did my dilation. So dilation worked the same. You're still multiplying your coordinates, but it's not going to be outside of the original image, right? So it just makes it look a little different, but the rules are applied the same way. So it just kind of showing you that you do the same thing, and it's going to look a little different. And then I just want to take a little look here at this little math talk question, where it says, describe how you can check graphically that you have drawn the image correctly. Well, I just did that, and I checked my side lengths. But you would also draw line segments connecting your vertices and making sure that they all intersected at the center of dilation, right? So that means they should all intersect at the origin. If I'm drawing lines through my points, they should all intersect at the origin. In this case, they do. So when I connect B prime and B, they should intersect at my center of dilation, which is, in this case, the origin. And they do. So that's one way to check also. So I need you guys to do your turn on your own, and we will check that in class tomorrow.